Hey everyone! Today, we're diving deep into a device you probably use every single day, but maybe don't think too much about: the humble microwave oven.
You know, it really does feel like a little bit of everyday magic, doesn't it? You put in last night's leftovers, you hit a couple buttons, and bam! A minute later, it's steaming hot. So how does this box use invisible energy to heat food, seemingly from the inside out? Well, that is the big question we're going to unpack today.
And to get to the bottom of this, we're not starting in some high-tech food lab. Nope. Our story begins way back, connected to World War II, with a top-secret military project and a very, very messy accident involving a candy bar.
So first up, we're going to explore this incredible origin story. We'll trace the microwave's path from a piece of secret military hardware to a fixture on just about every kitchen counter in the world.
This right here? This is the aha moment. Percy Spencer was a self-taught engineering genius. He was working on magnetrons. These are the powerful tubes that generated microwaves for Allied radar systems. And one day, he realizes that the same waves that could spot enemy planes from miles away could also melt his afternoon snack. He got curious. He tried it with popcorn kernels next. They popped all over the lab. Then an egg, which famously exploded in his colleague's face. And just like that, the age of microwave cooking had begun.
And this timeline just shows you what a wild journey it was. I mean, look at that first commercial model from 1947, the Radarange. It was an absolute monster. It was nearly 6 feet tall, weighed over 750 pounds, and had to be cooled with water plumbing. Can you imagine that in your kitchen? It took over 20 years of incredible engineering to shrink that beast down into the affordable, countertop-sized Amana model that finally made it into our homes.
Okay, so that's the origin story. But how did they actually turn that wartime tech into a kitchen appliance? Well, it all comes down to the engine that drives the whole thing, this amazing device called a magnetron.
Before you can even make a single microwave, you need power. And I mean a lot of power. There's a transformer inside your microwave that takes the regular voltage from your wall outlet and cranks it up to an insane 3,000 to 4,000 volts. That massive electrical push is what's needed to get the magnetron fired up. And the process itself is just brilliant. Here's how it works. First, a little filament heats up and boils off a cloud of electrons. Then, that super high voltage yanks those electrons toward a copper block. But, and here's the genius part, there are powerful magnets that force that stream of electrons to spin, like a tiny tornado. As this spinning electron vortex whips past these little cavities carved into the copper, it makes them resonate, generating a powerful, continuous wave of energy. It's kind of like blowing across the top of a bottle to make a humming sound, just on a crazy electromagnetic scale. So just to quickly recap the key parts, you've got the cathode, which is the electron source. You have the anode block, with cavities that are perfectly sized to set the frequency at 2.45 gigahertz. The magnets provide the spin, and then an antenna grabs all that energy and beams it into the oven.
All right, we've successfully created the microwaves. But what actually happens when those waves hit your food? This, my friends, is where the physics gets really cool. We're talking about a full-on molecular dance party.
The official scientific term for this is dielectric heating. You see, a regular oven just heats the air around your food, cooking it from the outside in. A microwave is totally different. It uses an electromagnetic field to generate heat directly inside the food by making specific molecules go nuts.
And there are two main ways this molecular dance happens. The first one targets water. Water molecules are polar. They have a positive end and a negative end, kind of like tiny magnets. The microwave's field flips back and forth 2.45 billion times a second, and it forces those water molecules to spin frantically trying to keep up. All that spinning creates friction between the molecules, and friction creates heat. The second method works on salts. The electric field grabs onto charged salt ions and just drags them back and forth, smashing them into other molecules like tiny bumper cars. All those collisions generate even more heat. It's why salty soup gets screaming hot so fast.
So, this molecular dance is incredibly powerful, but the way it works also leads to some pretty strange results. Let's dig into the common quirks of microwave cooking. You know, hot spots, scary sparks, the defrost button, and see how it's all tied to the physics we just talked about. Ugh, we have all been there. The plate is so hot you can't touch it. The edges of your food are like lava, but the center is still an ice cube. So why does this happen? The answer is actually in the nature of the waves themselves. So inside the metal box of your microwave,
The waves are bouncing off all the walls and interfering with each other. This creates a stationary energy pattern called a standing wave. And this wave has peaks with tons of energy, those are your hotspots, and it has valleys with almost no energy at all. And yep, those are the cold spots.
And get this, these spots aren't random. Physics dictates their exact location. At the frequency of 2.45 gigahertz, these hotspots are separated by a very specific distance, about 6.1 centimeters or 2.4 inches. So if a part of your burrito happens to be sitting in one of those cold spots, it's just not going to get cooked.
To solve this annoying problem, engineers came up with two really clever tricks. The one we all know is the turntable. It's a mechanical fix. It physically moves the food through those fixed hot and cold spots. But some higher-end models use something called a mode stirrer. It's basically a metal fan that spins and scatters the microwaves, which moves the hot spots around the food. Same goal, just two different ways of getting there. And what about the big one, metal in the microwave? We've all been warned never to put a fork in there, and for very good reason. Metal reflects microwaves, which is bad enough, but sharp points, like the tines of a fork, concentrate that electric field into an incredibly intense point. If that field gets strong enough, it can literally rip electrons off the air molecules around it, creating a spark of superheated ionized air or plasma. It's basically a miniature lightning storm inside your oven.
And finally, let's talk about the defrost button. You know why it's so frustrating? Because liquid water molecules are free to move, so they're fantastic at absorbing microwave energy and heating up. But in ice, those exact same water molecules are locked into a rigid crystal structure. They can't spin. This makes ice almost transparent to microwaves. So as soon as a tiny bit of your food defrosts, that little puddle of water starts cooking aggressively, while all the ice around it just sits there, staying frozen solid.
Okay, we've covered the basics, we've covered the quirks. Now let's get weird. The physics of microwaves can lead to some truly bizarre and, honestly, awesome phenomena.
Okay, a quick public service announcement here, because you need to be really careful with this one. If you have a very clean, smooth cup, a microwave can heat water past its boiling point without it actually boiling. It's in a super unstable state called superheating. If you then disturb it, like by dropping in a sugar cube or a tea bag, you give the bubbles a place to form, and the whole thing can flash into steam explosively.
And of course, we have to talk about the famous grape experiment. You might have heard the old explanation that two grapes act like an antenna. Well, the real science is actually way cooler than that. It turns out that each grape half is the perfect size and shape to act as a resonator for microwaves. When you put them right next to each other, they focus all that microwave energy into one tiny, intense hotspot right between them. It gets so powerful it ionizes the electrolytes in the grape skin and creates a spectacular jet of plasma.
All right, let's wrap this all up with some practical information, separating some of the facts from the fiction when it comes to microwave safety.
Okay, this is super important. The label microwave safe on a plastic container only means one thing. The container itself won't melt. It does not mean that chemicals won't leach out of the plastic and into your food. As a general rule, stick with plastics that have the number 5 on them. That's polypropylene. You really want to avoid microwaving in plastics marked #1, #6, or #7. And honestly, when in doubt, just use glass or ceramic. It's always the safest bet.
So the next time you go to heat up your lunch, just take a second to remember everything that's going on inside that box. It's a direct descendant of top-secret wartime radar, it's a miniature particle accelerator, and it's a molecular dance choreographer, all humming away on your countertop. It's pretty amazing what's hiding inside such an ordinary kitchen appliance, isn't it?